Hey, this is Mr. Leach with Simpson Math, and you're watching a video about linear regression. This video just works through a part of a single question, so it's just a demo about linear regression. The question is there a relationship between math SAT scores and the number of hours spent studying for the test? A study was conducted involving 20 students as they prepared for and took the math section of the SAT. On the right side of the screen, you can see the provided table. We have hours spent studying, and then the math SAT score. So that means that this first person studied 4 hours and received a score of 390. The second person spent 9 hours studying and received a score of 580, and so on and so forth. The first part of 6 in this video, determine a linear regression model equation to represent this data. There are several ways you could go about doing this. You can do this in Excel. You can do this online at desmos.com, D-E-S-M-O-S. You can also use a graphing calculator or some other statistical software. Today I'm going to be using a graphing calculator. Specifically, I'm going to be using the TI-Nspire. I am making an assumption that you are familiar with this graphing calculator or a graphing calculator that is similar to it. What's nice about the TI-Nspire is that you can title your data so that way you can find it easier. So our first task is to determine a linear regression. So to do that, I'm going to press the menu key, go to Statistics, perform some stat calculations, and then I'm going to pick the fourth one down, linear regression a plus bx. If you want to use the third one down, mx plus b, feel free. That corresponds with what you do in your algebra classes. I teach statistics, and statisticians, we like to use the a plus bx. The reason for that is for if we ever get into multiple regression where we have multiple x's, it sets the stage for that. So I'm going to pick linear regression a plus bx, press the right arrow twice, and up pops our list of variables. That's why we named them. Our x variable is hours of study. Press tab to get to the y variable. Hit the right arrow again and pick Math SAT. One thing of note, because we're going to be using this, it's going to store our regression equation into F1, and we're going to be able to recall that a little bit later. None of these things need to fill out, so you just click the OK button or hit the Enter key, and it calculated our regression equation for us. Because this is the a plus bx, our equation is going to be y equals 353.165 plus 25.3265x. So here's how I wrote down the equation. There are two key things that are different from when we just looked at it at the calculator. One is that you should see that we have the variable names described in the equation itself. I teach AP statistics, and one of the things that they have to do anytime they write down their linear regression is to define the variables. They can do so in the equation, or they can do it just to the side saying y is math SAT. To me, it's easier to have them be in the equation. So this hat means predicted. What that means is we don't know the actual y, but for a given x, we can predict a y based upon the model. That's going to be an important distinction in an upcoming question. Letters B and C we'll do together. We'll graph the new equation and then decide whether the new equation is a good fit to represent this data. Let's go back to the calculator. The best way to graph this is simply to use technology. So let's add a new page on our calculator. So let's add a data and statistics page. I hit Control Dock and add a data and statistics page. Wiggle your mouse around a little bit until your mouse is visible, and then move it to the bottom to click to add a variable. And let's add our x variable, hours of study. There's a nice little dot plot for us, but we want the scatter plot, so click to add a variable on the right side, pick Math SAT, and here's our scatter plot. Now let's find the regression equation. Press Menu, Analyze, and then Regression. And there's a similar list to what we saw earlier. Again, I'm going to pick a plus bx. So pick Show Linear, and it graphs the line for us, and there's the same equation that we saw a second ago. If you were to graph this line by hand, I would graph a point on the low end and a point on the high end. Using the calculator, press Menu, Analyze, and go down to Graph Trace. Using that graph trace feature, I can see that there's a point at about 2,400 and a point at about 18,800. If you were to be graphing this by hand, it's a rough sketch anyway, so plot your points as best you can, put a small dot at 2,400 and a dot at 18,800, and use a straight edge to graph the line. Letter C is to decide whether the new equation is a good fit to represent this data. Here's a few tips. First, look at the scatter plot and just does the scatter plot appear to be linear? If there's an obvious curve to the data, especially if it looks exponential or quadratic or logarithmic, it'd be pretty easy to tell with some of those curves. Another option is the graph might need to be subgrouped up. Year data tends to do this. There tends to be an increase, maybe a plateau, maybe a decrease, and those things would maybe need to be chopped up. So if the data is not linear, you have no business doing a linear regression. Then if it appears to be linear, we need to create what's called a residual plot. If the data appears to be linear and the residual plot is fine, then we can look at r and r squared to determine how strong of a fit it is. Let's go back to the calculator. So click on Menu, Analyze. Now that we have a regression, we can look at the residuals. So pick Residuals, and then Show Residual Plot. What a residual is, it's the distance and direction from the line to the point. So this dot right here is the same dot here on the graph. Notice it has the same x value, but its residual is a negative 57.1. This student underperformed by 57.1 compared to what we would expect for someone who studied for 12 hours. While this student here scored about 34 points higher than we would expect for someone who's studied for 8 hours. What we're looking for in the residual plot is we want to see no apparent curve or pattern. This does do a pretty good job. There is a slight bit of a curve, and that's due to this outlier. This outlier is bringing that line down a little bit more than what we'd expect, and also probably an indication that a line might not be a best fit. I actually went ahead and ran a power regression that created a curved pattern that was almost a cube root that actually fit this data a little bit better. But overall, this does do a pretty good job, this outlier withstanding, of being linear. If this outlier were removed, this data would be very linear. Secondly, we can look at r and r squared to see how strong of a relationship there is between x and y. Going back to our table, we see that r is 0.9336 and r squared is 0.8716. Here's just a little summary about r and r squared. This r is actually a very nice r. It's pretty strong. It would fit in what we would call strong. If it was around 0.7, we'd call it moderate. Around 0.5, we'd call it weak. R is a number that falls between -1 and +1. If it was +1, it would be perfectly linear and positive. If it was -1, it would be perfectly linear and have a negative slope. If it was 0, there would be no correlation. So this is actually a pretty strong fit. One thing that my students have a hard time with is this just tells us that the linear relationship between x and y is pretty strong. This does not prove that it's linear. What we did by looking at the residual plot helped us sort of kind of zoom into the data to actually prove to ourselves that the data is linear, because when you graph a line through the data, there wasn't an apparent curve. The other thing we can talk about is r squared. This is quite literally r squared. If you square 0.4929, you should get about 0.8890. What we can say about this is this sentence: 88.9% of the variation in math SAT scores is explained by the variation in hours spent studying. Now, this doesn't mean that hours spent studying causes the math SAT scores to go up. What this means is, as I look from person to person at the different hours that they're studying, the changes that we see when I move from person to person only really explains about 89% of why the y might change. So that means is that we could find about 11% of other x variables that could add on top of the hours spent studying. Things like their intelligence or how hard they worked in school. These various x variables we can put together and ultimately get pretty close to that 100%. Interpolate data. If a student studied for 15 hours based on this study, what would be the expected Math AT score? Well, simply, you take the 15 hours and you plug it into hours studying and simplify. So plug in the 15, multiply it by the 25.33 and add it to the 353.17, and we get the predicted Math SAT to be 733.06 for someone who studied for 15 hours. Let me show you this on the calculator. So I added a calculator page. Remember how earlier I said that the regression equation was going to be stored in F1? Well, if you press the var key, there's F1 right there. So if I type in F1 of 15, I will get the 733.062. You also could have literally typed in F1 of, notice how that pops bold, that's a little dude in the calculator saying, I know what that is. So let's do another one. Let's say if someone studied for 12 hours, what do we predict? That they should get a 657.082 on the SAT. Letter E, interpret data. If a student obtained a Math SAT score of 720 based upon the study, how many hours did the student most likely spend studying? So at a first glance you think, oh, this is similar to what we saw in the last question, just turned around. It's tempting to plug in 720 in for Math SAT and solve for our studying. That's an easy solve, that wouldn't be too hard to do. The problem is this, we are predicting the Math SAT when we know our studying. We can't predict our studying based upon Math SAT with this equation. We need to go to our calculator and generate another regression equation, this time predicting our studied based upon Math SAT. I'm back on my listen spreadsheet page. I have my cursor in column D because the calculator output would be put into the next column over in column E by default. So press Menu, Statistics, Stat Calculations, Linear Regression A plus BX. It's the same thing we did earlier, but this time I'm going to have my X variable be the Math SAT and have it predicting the hours studied. This time, notice it's going to save it in F2. So we have our new equation, negative 10.94 plus 0.0344x. So here's my new equation. Our studying hat equals negative 10.9411 plus 0.0344 times the Math SAT. Well, from our question, our Math SAT score is 720, so plug that in, and we end up with 13.838 hours. One note is if I would have plugged in 720 into the predicted Math SAT in hopes of trying to predict our studying, this model would have predicted 14.4843 hours, not 13.838 hours. That's a pretty significant difference. So it's important that you know that these regression equations are one-way equations because these y variables are the predicted value. Last question. Extrapolate data. If a student spent 100 hours studying, what would be the expected Math SAT score? Discuss this answer. So this seems like the question from D. So just plug 100 hours into hours studying, simplify, and you get 1340.46. Now what's wrong with this? Linear regression does not provide the capabilities to go far beyond the domain of our data. So 100 hours is beyond the domain of the data, and on top of that, 1340.46 is an impossible Math SAT score. I believe the maximum SAT score one could get in a single subject is 800, so this is obviously not a good fit. Back on the calculator, I zoomed the window out to 100. We can see that it is way beyond the scope of the data. This line has no business trying to predict anything this far out here. This outlier tells a bit of a story. The student studied for 22 hours, only was 20 points higher than someone who studied for 16 hours. What's going to tend to happen is studying a little bit is going to help some, but studying a lot isn't going to help as much. Also considering they were 10 points away from a perfect math score, meaning there's not much room that they could have gone up. So it was impossible for this student to get their predicted value. So this regression actually has a hard ceiling, and so the rest of these data values are going to have it kind of a horizontal asymptote with respect to that hard cap of 800. So for the domain of our data, it is reasonably linear. But if we go much beyond most of our data, really even out to this outlier, we're going to be getting into impossible solutions. So in today's video about linear regression, we saw how we could find the linear regression using a calculator, how we can graph it, decide whether it has a good fit or not, interpolate the data working with that equation, and then finding out that it is not a good idea to extrapolate beyond the domain of our data.